Now have a look at equation 2 and 4. Equation 2 and 4. We are going to equate the coefficients of equation 2 and 4. So we get dou G by dou T at constant pressure Ni, which is equal to minus S. Here we have equated dt terms, right? By equating dp terms, we get dou G by dou P at constant temperature Ni, which is equal to V. Okay, so we got two more equations, equation 5 and 6. Now we are going to differentiate equation 5 with respect to Ni. So what will we get? Dou by dou Ni of dou G by dou T at constant pressure Ni. Again we are applying conditions. Constant temperature, pressure and Nj, which will be equal to derivative of this term, right? Minus dou S by dou Ni at constant temperature, pressure, Nj. So we are differentiating equation 5 with respect to Ni. So dou by dou Ni of dou G by dou T at constant pressure Ni, again conditions, constant temperature, pressure Nj, which is equal to minus dou S by dou Ni at constant temperature, pressure and Nj. So what is this term? Variation of an extensive property with respect to number of moles of a component at constant temperature, pressure and constant composition of other components. What is that? It is partial molar entropy, right? Partial molar entropy of ith component. So it is Si bar. So here is a minus symbol, so minus Si bar. Okay. So dou mu I by dou T at constant pressure Ni is equal to minus dou S by dou Ni at constant pressure, temperature Nj, which is equal to minus Si. So you obtain this term from here, right? Here we are going to exchange between dou T and dou Ni. So we get dou by dou T of dou G by dou Ni. What is that? Dou G by dou Ni is G bar I, that is chemical potential. So this term, entire term becomes dou mu I and dou by dou T of mu I, that is this one, dou mu I by dou T at constant pressure Ni is equal to this term minus Si bar, that is equation 7. According to equation 7, at constant pressure and composition, the rate here, constant pressure and composition, the rate of variation of the chemical potential of a component I with temperature is equal to partial molar entropy of I. Okay, so here as you see here, at constant pressure and composition, the rate of variation of chemical potential of ith component with respect to temperature is equal to, what is it? It is partial molar entropy of ith component. Since S is always positive, it is seen that the chemical potential decreases with increase in temperature. But the extent of decrease in Ui depends on whether I is a solid, liquid or gas. Okay, so the change in entropy and Ui change would depend on the state of the sample or matter, whether it is a solid, liquid or gas. The effect of temperature on chemical potential can also be expressed in a form similar to Gibbs-Helmholtz equation. So this is our Gibbs-Helmholtz equation. G is equal to H minus Ts. So let this be equation 8. We are going to see another mode of representation of variation of chemical potential with respect to temperature from Gibbs-Helmholtz equation.